All right, so our next speaker is Edson de Faria, and he's going to talk about asymptotic, holomorphic dynamics, and renormalization.
Okay, so thank you very much. Thank you for the, the organizers here. Ara, Dragomir, Mahmoud. So it's a pleasure to be back here. I can't believe I've been 10 years away from, almost 10 years away from this place. Well, I'm also a frog, but I'm an old frog, so I can't really jump. So I can only see very close to where I am, okay? So this topic, well, first of all, everything I'm going to talk about is joint work with Trevor, who unfortunately is no longer doing math. He went to machine learning and stuff, and with Sebastian, who is a professor at Imperial College and is a real expert in one-dimensional dynamics. And the subject is, as
he was supposed to be here, but
yeah, but he had a surgery, an operation. So yeah. So anyway, so the themes in this talk are well, the dynamics of certain maps that are called asymptotic and holomorphic. I'll explain what that means, and the relationship with renormalization of one-dimensional maps. Okay, unimodal maps, more specifically, and in some sense, this is going to be, the results are not, they are to be expected. What's sort of interesting maybe is some new techniques that are used, okay? So there is a saying that what is it? Is the proof of the pudding is in the eating. Isn't that what you say? And so what's really interesting is happening in the proofs, but I'm not going to give you the proofs. So, so there is a history which unfortunately is at the end of the slide. So if there is some time at the end, I can tell you some history about how the problem of renormalization came about and the various contributions, okay? So first I'm going to define what I mean by asymptotically holomorphic. So these are maps which are defined on some open set on the Riemann sphere. It could be on a Riemann surface as well. So it's a continuous map, and you fix some r greater than 1, and you assume that there's some forward invariant compact set for this map, okay? And you say that f is asymptotically holomorphic of order r near this invariant compact set. Well, first of all, f has to be CR. F has to be a quasi-regular map. So what is a quasi-regular map? It's a map which is locally quasi-conformal, okay? You saw, I think, in Dick Cannery's talk, maybe, the notion of quasi-conformality, right? Quasi-conformal homeomorphism is something that maps, infinitesimal circles into ellipses with bounded eccentricity. So the ellipse has like an angle and has a number which is the ratio of the minor to the major axis. So that gives you a complex number called the complex dilatation of the map. And being quasi-conformal means that the L infinity norm of this dilatation is bounded away from 1. I call this dilatation, this is the dilatation, mu f of z, okay? And being asymptotically holomorphic near this invariant set means that as you get closer and closer to the set, the map becomes closer and closer to being conformal with a specific rate, okay? It turns out that if I give you a map on the line, okay, which is CR, there's always an extension to the complex plane which is asymptotically holomorphic of order R in this sense, okay? And for me, the lambda, the invariant compact set that I'm interested in this talk is going to be an interval.
Is R an interval?
Sorry? R is a real number, okay?
A real number.
A real number, yes. So CR means, if R is a fractional, it means, let's say R is n plus something, plus beta. So then it's Cn, okay? It's a Cn map with highest derivative is holder of exponent beta. Okay?
But it's not true to me if you're talking about branch covers. You
Yeah.
say quasi-regular math.
Yeah, these are like branch covers, yeah. They are, they will be. In fact, they'll be even more special. I'm only interested in maps which are polynomial-like. I'm going to draw a picture. So, like I said, mu of f is the dilatation of the map, okay, the complex dilatation. So what is an asymptotically holomorphic polynomial-like map, which is the kind of map that I'm going to be interested here. So in this case, you have two Jordan domains, actually two disks. If you think of topological disks, one compactly contained in the other. The smaller one is the domain of the map. The larger one is the codomain, and the map is a proper CR map. Okay, so onto. I'm going to be assuming in this talk that R is at least 3 for reasons that will become clear later. And I assume also that I have some forward invariant compact set contained in the so-called Fielding-Julia set of this map. Okay? I didn't say it here yet, but the map is supposed to be a branch cover with one branch point, with one critical point. This is going to appear in a moment. So the Fielding-Julia set is basically just a set of points that you can iterate forever without falling into the annulus v minus u. Okay, when you fall in there, you can no longer iterate the map, right?
So sim plus f is z equals to z to the n?
Yeah, for example, you can think of an actual holomorphic polynomial-like map, which is like z goes to z squared on a disk of radius greater than 1, okay? So to be asymptotically holomorphic polynomial-like, which is a mouthful, I'm going to abbreviate it by using the acronym. I don't like acronyms, but I'm going to be forced to use it. So an AHPL map is a map which is a degree D branch covering map of U onto V, branched at a unique critical point of some degree. The degree has to be an even integer. Which is also asymptotic.
Why by assumption or why?
Sorry?
Why does it have to be an even integer?
Because I want the real, I want the map on the real axis to be a unimodal map.
Oh, okay.
Yeah. Okay.
That's why we assume it.
Right, that's why I'm assuming it, yeah. Okay, and I want the map to be asymptotically holomorphic of order R near this invariant set, which I'm actually assuming that contains the critical point. And once it contains the critical point, since it's forward invariant, it contains the entire post-critical set of the map. The post-critical set is just a closure of the forward orbit of the critical point. Okay. So, so that's the observation there. But this is all a bunch of words and symbols. So let me give you a picture. Okay. So here's the picture. So you have this disk, this topological disk U, okay, which is the white disk, and you have this gray disk, which is V. The map F maps F onto V, okay, and it's branched at this point here. So there's a critical point here. And the blue set, I'm drawing it as if it were some curve. Doesn't need to be, but so this is the blue set, okay. We will be interested only in the case where the map is symmetric about the real axis, and this blue set is actually an interval, okay. So I'm assuming that the blue set is forward invariant, and the map has to be more and more conformal as you get closer and closer to this blue set. And this tree-like set that you see here, which doesn't need to be tree-like, I drew it like that, but anyway, this is the Fielding-Julia set. This is the set of points that you can iterate forever, okay? I'm drawing it like a tree because it turns out
Does it always fall onto the blue? Eventually?
Eventually.
Eventually.
Well, there are lots and lots of periodic points which never fall into the blue set. But what you said is true in the sort of like maybe in the measure theoretic sense. Almost every point in the Julia set, if the Julia set is measured, positively measured at all, has an orbit which is forward asymptotic to the forward orbit of the critical point. So almost every point is actually going to converge to the post-critical set. Okay, but this is a theorem which we don't really need here. By the way, this theorem is for holomorphic maps. So these maps are not holomorphic, so you have to be careful with this. Every such map,
in general, that blue thing can have like intersected.
it could be, in principle, it could be any compact set which is forward invariant. Okay, but in our case, it's going to be an interval.
There was a delta in that earlier picture.
Oh yeah. This is just okay. So I'm saying that if you're delta close to the blue set, then the dilatation of the map should be of the order delta to r-1. Okay, so it's sort of going to 0 as you get closer and closer to the blue set with this rate. Okay. So every quasi-regular map admits what we call a Stoilov factorization. So it can be factored as a composition of a quasi-conformal diffeomorphism in this case, and a conformal map which is actually in this case is going to be a bona fide polynomial-like map. Okay, polynomial-like map is a holomorphic map that has this picture that maps a disk onto a larger disk with a certain degree branched at a certain point. Okay. And this decomposition is essentially unique. Okay? I mean, if you normalize some points, it's really unique. And this, in this case, this phi is not merely quasi-conformal, it's actually asymptotically holomorphic. Near where? Near the image under G of the set that I called lambda before. Okay? But in our case, G is going to preserve lambda, so it's going to continue to be asymptotically holomorphic around lambda. So here's a warning. These maps are not uniformly quasi-regular. This is a very different theory. If you have, what is a uniformly quasi-regular map? It's a map which is quasi-regular in the sense that it's locally quasi-conformal, and all of its iterates, you know, the dilatation of all of its iterates is uniformly bounded. Okay? These mu's for the iterates are uniformly bounded away from 1. When you have such a uniformly quasi-regular map, studying such maps is essentially the same thing as studying holomorphic maps. And in fact, the reason is, I mean, I think Dennis was the guy who proposed this trick, where if you have a quasi-regular map which is uniformly quasi-regular, you can look at the dilatation along an orbit. This is going to give you a lot of points inside the unit disk, and you can take the barycenter of those guys. This will give you some mu inside, which is invariant under the map, okay? And then you can, so you have now a quasi-regular map that preserves a certain quasi-conformal structure. You can use the measurable Riemann mapping theorem, and you obtain conjugacy to a holomorphic map. So studying these maps is the same as studying holomorphic maps. But the maps we are interested in are definitely not uniformly quasi-regular. In fact, not even locally. If you think about it a little bit, suppose you have a fixed point of the map which is contracting, say. So it's taking a disk to a smaller disk. Okay? Now imagine that you have a map like one of these that is also has an attracting fixed point, but the fixed point has two different eigenvalues. Okay? So the disk is going to be mapped to an ellipse, and as you iterate this picture, the ellipse is going to get thinner and thinner and thinner. So the moduli of the annuli that you have on this picture, they go to 0, okay, or to infinity, depending on how you look at the modulus. So whereas for the holomorphic map with an attracting fixed point, the modulus stays constant as you iterate. So these maps are not even locally conjugate to a holomorphic map, okay? Locally quasi-conformally conjugate.
But away from that critical point, then everything is invertible and it's locally quasi-conformal, right?
What do you mean? I mean, away from the critical point? Away from the critical point, the map is a local homeomorphic diffeomorphism. Yes. Yeah, but it's not uniformly. As you iterate, you see.
But locally quasi-conformal.
No, but you have to iterate anyway, right? To find a conjugacy. To find a local conjugacy, you have to iterate anyway, right? So, and these maps are also not Another class of maps that was introduced by Fred and by Dennis a long time ago is maps which are called UAC, uniformly asymptotically conformal. This means that if you take a point and you look at the inverse branches, you know, the full pre-orbit, as you go along the various branches, your map, you know, the compositions are uniformly quasi-conformal, okay? This doesn't happen here either. So you really need different techniques. But you might ask, you know, why study these objects? Right? I mean, so the reason is renormalization. We are interested in understanding renormalization of unimodal maps. And there is a fairly complete theory for real analytic maps. This starts with Dennis. It's fundamental. I mean, everything starts with Dennis. I mean, almost everything.
You have to live with it.
Okay. No, but I mean, I feel like, especially in this area, Dennis is like the guy who kind of blazes the trail, and we are just going after him, like trying to asphalt the road or something. So, but here there are contributions by many people. So Dennis started, and then actually Dennis used some of the theory of Duadie and Hubbard, the polynomial-like maps.
I would say they started.
No, but I mean,
they gave some nice ideas. Yeah.
No, sure, but I
they
don't.
formulated questions.
But they didn't formulate the connection with renormalization, maybe, right? This is you.
No, they did.
They did?
Yeah.
Well, so sorry about that. Maybe I should put Duadie Hubbard first. And
Yeah.
But I don't know about that. Anyway.
No, but it was, you know, it's this French thing. Duadie was, you know, we used to say if you can get Duadie interested in your problem, it's half solved. And Hubbard got him interested with these beautiful pictures of the Mandelbrot set, Julia sets, and got him interested. He's a wonderful complex analyst. So it was like a fantastic. And the first thing they did in the first week was to formulate beautiful questions, like the Fatou question. I mean, I heard about the Fatou question, which I later solved.
From their lectures.
From the from talking.
I
They
see.
gave a lecture, and they gave a beautiful presentation of these dynamic questions. And
But
by the weekend, I was totally sucked in for years. Yeah.
But what about this fact that you know, quadratic-like maps say they can be renormalized under certain circumstances? Isn't that your picture? No.
First of all, the physicists considered the language comes from.
Oh no. For real one-dimensional things, I agree. But I mean, I'm talking about the complex picture of, you know, that you can actually.
No, that comes from them as well. From the pictures, see, when Hubbard wanted to interest undergraduates in showing how an interesting, simple-sounding math problem, like solving for the zeros of a cubic polynomial, finding the zeros of a cubic, which in history of math is not uninteresting, in the Renaissance, Middle Ages, right? Cardano and so on. And he used Newton's method, which is an iteration scheme. And you can see in Newton's method on the parameter plane, choose family of cubics depending on one parameter, little Mandelbrot sets appearing.
Okay.
And so Newton's method could be thought of, if you started there and did Newton's method, you would get a quadratic-like map by some iterate. And so when you composed the map and came around, you were back in the quadratic picture of dynamics again. Well, that's what renormalization is.
Yeah.
But renormalization, that's just called renormalization. I mean, dynamics, people in dynamics have, starting back to Poincaré, have studied first return maps. But the idea is that you can still, the idea that you borrow from them is that the renormalization issues, which from the physicists were involving, they made an analogy between iterating a map till the critical point comes back and looking at it locally to the renormalization they do in physics, where they go from a very fine scale, they average up to a coarse scale. So the idea was iterating the map is like going and then looking at it magnifying glasses. And they use that language of renormalization, right? But as an induced transformation or a first return map, it was in dynamics. But they saw it, these Mandelbrot sets, inside the general picture of renormalization.
Okay.
And so, and then they also had characterized this quadratic-like map picture, which is what you're talking about. So that was their idea.
Okay.
Yeah. And then
So,
when you want to prove something, though, at the last step, you have to use that power, right? Yeah.
okay.
Every story of the history of ideas is sort of not known. I'm for the younger generation now, because you look at papers, and
Yeah.
first of all, the dates are wrong, because the papers appear often years after when the ideas were understood, so the dates are already wrong. So then you decide, oh, this is the earliest paper that has this, so it's due to this person. That's the first thing that's wrong.
Okay.
You have to say, to my knowledge, this is due to this person.
Yeah, okay.
That is correct. You know,
Okay, let me continue then. So there is this theory, okay? I'm not going to talk about it.
I mean, dualité was kind of the Thurston of complex analysis in all dimensions in France, you might say. Okay.
Okay. Okay, so but once you have, you know, the full picture, there's something called the renormalization operator. I'm not going to get into this, and there's a lot of work trying to show that this renormalization operator, whatever it is, oops, it's here, is
First return map to small scale.
yeah, renormalization dynamically is what Dennis said. You know, when you say that a map is renormalizable around some point, if there's some neighborhood of this point, which you can iterate and returns to this point after a finite number of iterates, you know, have this joint chain, you get back, and when you get back, the return map is of the same type that as the map that you had started with. So if you start with something which is polynomial-like, you want the first return map to be polynomial-like as well. So that's what renormalization is from the dynamical standpoint. So anyway, there's a long and beautiful story to be told here. Okay, so it starts, I mean, the part that I'm interested in, it starts with Dennis and what he covered. And Dennis was he established, I'm going to state this in more precisely later, but he proved, among other things, he proved the existence of an attractor for this renormalization operator. And he even was able to prove convergence towards the attractor, but not at an exponential rate. The exponential rate was obtained by Kirk-McMullen. And then later, Lubitsch, who had already proved some combinatorial rigidity theorem that established like the expanding direction of renormalization, he was able to actually put everything together, and he obtained like he showed that the renormalization operator is hyperbolic, but it's on a very funny space. It's a space which is of quadratic-like germs, modulo affine conjugacy. And that's something that has a very crazy structure. It's a manifold, but it's not a manifold model on a Banach space. It's not a Banach manifold. It's a manifold model on topological vector spaces which arise as direct limits of Banach spaces, of analytic functions. So it's a long and complicated story. More recently, Lubitsch and Arthur Avila, they were able to kind of get the complete picture, you know, for unbounded type and also for all sorts of even integer exponents for these maps. So anyway, so there's a long story, but there is also the CR world, and the CR world is of course much larger than the real analytic world. And you would like to know that renormalization there is also something which is hyperbolic in some sense, but then you start running into a lot of technical problems because renormalization involves composition, and composition is notoriously ill-behaved, you know, from the point of the differentiable viewpoint. It's not a it's just a continuous operation. Okay, it's not even Holder continuous unless you. So, anyway, it's a long story, but there is a work of this functional analyst, Davy, in 1992. He was able to prove something about C2 plus epsilon maps in the period doubling case. I'm going to, maybe I'll mention that later. And then, in collaboration with Wellington Di Mello and Alberto Pinto, we wrote this paper where we kind of used some of David's ideas and combined them with something that is in Lubitsch's work. I mean, a lot of what's in Lubitsch's work, to kind of transfer this hyperbolistic from the real analytic world to the CR world. But the problem with this paper is that it's very ugly. I don't like it. Okay? It's like it's 100 pages and it's like yes. So anyway, I was never happy with that. So I teamed up with Sebastian, and the hope was to try to say, okay, there are these beautiful techniques that are used in the analytic case. When you're studying real analytic maps, you can complexify, you can use all sorts of things. You can use Schwarz lemma, you can use Teichschneider theory, you can use a lot of stuff. So why not try to do that in the CR case too? And that's why we are interested in these asymptotically holomorphic maps, because every CR map has an asymptotically holomorphic extension. In fact, it has infinitely many. And it turns out that as you renormalize, you still get the same sort of picture. You get bounds, you have complex bounds. I'm going to talk about it. So let me try to explain, well, okay, so this is the renormalization picture, and that's the motivation, but that's not what I'm going to talk about. I'm going to talk about something much more elementary. We want to understand the basic dynamics of such maps, okay? So there are lots of questions that you can ask about these AHPL maps. You can ask, for example, the most basic thing is, are the repelling periodic points dense in the Julia set? The Julia set, by definition, is the boundary of that set that I call the filled-in Julia set. Okay? And this is a fact which is known for every rational map, or for every, in particular, also for every polynomial-like map, because polynomial-like maps turn out to be quasi-conformally conjugate to actual polynomials. Okay? So the answer will be yes, but you know, why is it true? I mean, the traditional proof of this fact for rational maps uses Montel's theorem, and we don't have Montel's theorem here. Okay, we don't have normality here.
You're assuming no attracting periodic objects in the filled-in Julia set.
Well, I'm talking about the Julia set, not the filled-in Julia set. See. You're not going to find an attracting periodic point in the Julia set. Okay, so another question you can ask, it's kind of a more topological question, is when is the Julia set locally connected? Okay, or maybe you can ask, what is the interior components of the filled-in Julia set? They're permuted by the map, and there are some periodic cycles. There may be some periodic cycles. And you may ask, if you look at a periodic cycle, which we call a stable component, what are the possible dynamics inside such a component? Okay, so can you classify them? So there is a classification. It starts with Fatou and Julia, and I think ends with maybe with Dennis. Well, these stable components. In particular, you can ask also, can such a map have wandering domains? Dennis proved that for rational maps, there are no wandering domains. Okay, the Fatou set doesn't have any wandering domains. It's a very beautiful paper. But here, in principle, there could be wandering domains. So you have to be, I mean, if you just formulate the question like that, the answer is immediately no, because away from you see, the map is asymptotically holomorphic. Away, it can be anything. So you might be able to do some surgery and produce some wandering domain far away from this invariant set, this forward invariant set lambda. Okay, but we are going to show that as we zoom in, and start getting closer and closer to the critical point, there is this thing called renormalization, and the renormalized maps they will not have wandering domains. Okay. Well, I don't want to go into this too much, but there is something called the pullback argument. Okay, and you can ask if there is a pullback argument here in this context. Pullback argument is something of the following type. Suppose you have two maps of this type, and suppose that they are conjugate on the real axis. Let's say by a quasi-symmetric map. So you'd like to say, well, is there a quasi-conformal conjugacy between them? Well, like I said, this is hopeless because because of what I said about the fixed points and all that. But you can ask, maybe there is a topological conjugacy, just a topological conjugacy, okay? So, anyway, so these questions they're not really obvious. So, but if you impose some conditions, okay, because the idea here is to start something, right?
Can you do an asymptotic, for instance, the Yoko's puzzle?
What?
The Yoko's puzzle.
What about the Yoko's puzzle?
Can you do asymptotically on yourself?
We can show, if we assume that the map is infinitely renormalizable, this is what we're going to say. We actually are able to show that the puzzle pieces shrink.
Okay.
And therefore the Julia set is actually locally connected. We are able to prove that it's always locally connected.
Yeah.
So, but for this to happen, we need to put some very restrictive hypotheses. We need to look at maps which are infinitely renormalizable. And then these facts are going to be true, but they're going to be true only for the deep renormalizations of these maps. Okay? All right, so let me let me skip the theorem. I'll come back to it because I know that Dennis doesn't like it says statements are stupid. The arguments are what really matter. So I'd rather well, I need some notation. I'm sorry. So I'll define what renormalization means now, and I'll draw a picture, and I think it will be very clear with the picture. So like I said before, renormalizing a map, let's say a map in dimension 1 here now, a unimodal map, okay? Let's say we have a unimodal map with a critical point at 0, You can even think of it as being a symmetric map about 0. So such a map is said to be renormalizable if you can find some little neighborhood of the origin which returns after a certain number of iterates to itself. And when you look at the return map, it is again unimodal, okay? And
Did you say yet what unimodal was?
Yeah, I didn't say what unimodal was. So unimodal is a map which has just one critical point in the interval, and it's. I'm sorry for erasing this beautiful picture here, but anyway. So unimodal map is something like this. Okay, it has one critical point. Okay, and there's various ways you can normalize these things. In a lot of places in the theory, it so happens that you need to normalize so that the critical value is at the boundary. Okay? Anyway, so unimodal means one critical point, and then there's two monotone branches. Okay. So the renormalization of a renormalizable map is you do the return map, and then you rescale to the original size. Okay? So you get this formula. And I also require these intervals in between. There's this chain of intervals. You start iterating. These intervals have to be pairwise disjoint. Okay?
Am I reading that correctly? F to the power p of the origin is on the, you get the endpoint lambda?
Yeah, lambda is by definition this guy here.
Okay, and then that's that f raised to the power restricted to minus lambda.
Yeah, it's an iterate. You're iterating p times. Yeah? You're restricted to this interval. Okay?
But those endpoints are coming from that lambda there.
Right. Yeah. Yeah. Anyway, so it may happen that when you renormalize a map, the map that you get is itself renormalizable. So you can calculate the renormalization of that. So that's the second renormalization of the original map. And you can keep going if the map is... So we are interested in maps which are infinitely renormalizable. Okay? And moreover, we are actually interested in, for this talk, I'm only interested in maps which are infinitely renormalizable of bounded type. That means that these periods, as you renormalize, these guys are called renormalization periods. P is small as possible, okay? Okay, so these P's are called periods, renormalization periods, okay? And if they form a bounded sequence, we say that the map is infinitely renormalizable of bounded type. Anyway, so here's a picture because it's better to do. So here's the interval 0, 1, I mean -1, 1, and here's 0, okay? which is the critical point. And you're supposed to imagine that there is a self-map of this interval, which is unimodal, with the critical point here. Being renormalizable of period 4, say, means the following. You can find a little interval around 0, okay? And 3 other intervals, these 3 intervals here, okay? Disjoint. And the map does the following. The map takes the red interval onto the rightmost interval. The rightmost interval comes to the leftmost interval. And then you go on, and there's a permutation there, until you come back. And then when you come back, that's your return map, and then you rescale this map. So the rescaled map is the renormalization. Okay, so this gives you an operator on some domain. I mean, actually defining the domain appropriately is a little bit of a problem. And you're interested in the dynamics of this operator for various reasons that I'm not going to go into. But you're interested in particular in finding an attractor for this operator and showing that it is a hyperbolic attractor in the sense of Smale, okay? Well, there's some notation. I don't know if I'm going to really go into this, but okay. So let me just draw another picture here. I should have drawn this before, but so now you're supposed that you have to imagine that you have an infinitely renormalizable map. And let's say we are in the so-called period doubling situation, where all the periods as you renormalize are always equal to 2. So you start with the original interval, and inside there you find 2 subintervals, one containing the critical point, and then you keep going. Inside this, each one of these you find 2 other intervals, and then 2 other intervals here, 2 other intervals here, and so on, okay? I'm very bad at drawing, but anyway, okay? And you keep going. And you sort of suspect that you're going to get a Cantor set, right? But you need to prove that. And Dennis was the guy who proved that. So anyway, there's a notation. If you look at the nth renormalization, you can write it like that, where the scaling now, the scaling is okay, so Qn is the product of the periods as you renormalize, okay? So if you renormalize 4 times in that picture, you're down to, I don't know, 16 intervals. So the Q, corresponding Q is 16, okay? And, oops. And the scaling factor is always the corresponding image of the critical point, okay? So like I said, these guys are called periods, and a map is renormalizable bounded type if these periods are bounded, and if you take the union of these intervals at each level, and then you take the intersection of these sets, you morally are getting a Cantor set, which is the post-critical set of the map. Okay, it's precisely the closure of the forward orbit of the critical point. Okay, the critical point, the forward orbit of the critical point is dense on this set.
You're using the bounded type here to conclude that?
No, this is actually always the case. What I'm not saying anything about is about the structure of this set. Okay. But in the bounded type case, I'm going to state a theorem which is due to Dennis, but which is stated in a different way. I mean, Dennis needs less hypothesis than I'm putting here. The reason for assuming C3 is because I want the renormalizations to be bounded in the C2 topology as we renormalize the map. And why do I need that? It will become clear later, I hope. So Dennis proved a result which is, if you put it in technical terms, is basically saying that this Cantor set has bounded geometry. Okay? It's saying that the ratio of each parent to the corresponding child is bounded, okay? Cannot be too big. And moreover, you get more than that. You get that the connecting maps, you see, if you fix a generation here, there are these arrows going around, right? There's iterates of f taking these intervals, some of these intervals to the others, I mean every interval to every other interval. So if you look at the connecting maps, they have this nice bounded distortion estimate here, okay? All right, and from that you can actually deduce, if you assume that the map is C3, you can deduce that the renormalizations are uniformly bounded in the C2 topology. And moreover, these bounds, they actually, this last paragraph here is to imply that as you renormalize, the deep renormalizations actually have bounds that do not depend on the map. They depend only on the bound of the combinatories, on the bound on the periods. Okay. Anyway, this is a very nice result, and it's the basis for everything that is done in this theorem. Okay? But like I said, it is better to, rather than try to, memorize the statement or something, just think about it in formal terms. So it's saying that the post-critical set is a Cantor set with bounded geometry. It's saying that the successive renormalizations of the map are uniformly bounded in the C2 topology, and that the bounds are becoming universal at sufficiently deep levels. This is what Dennis used to call, I think maybe he calls, bow bounds. There is an in-joke here which I'm not going to go into, but which has to do with Feigenbaum, but anyway. So Dennis also went much beyond that. He also proved something called the complex bounds. So imagine now that your maps are real analytic. You look at the little complex analytic extension to a neighborhood of the interval in the complex plane. You can start playing with that, and you can renormalize in the same sense. You can compose, and you show that eventually you get maps which are quadratic-like, or polynomial-like maps, or quadratic-like maps in the case of quadratic critical point, with good bounds. I'm going to draw a picture also. So these are the complex bounds, and just like the real bounds, the complex bounds also have this bow property. They also become universal, independent of the map as you renormalize. Okay? So there is a formal statement of the complex bounds, which I don't want to go into. Okay? Rather than going through this, let me give you a picture. Oops. So let me give you a situation. So but anyway, we need to understand something here. You start with something which is asymptotically holomorphic. So this version of the complex bounds was not proved by Dennis. This is a consequence of a more general theorem that was proven by Trevor Clark, by Sebastian, and by Sofia Trejo, who was a student of Sebastian, and unfortunately is also no longer doing math. She's also in artificial intelligence or whatever. So anyway. But the theorem is going to say something about deep renormalizations of these maps. Okay, it's going to say that they become these asymptotically holomorphic polynomial-like maps. And moreover, these asymptotically holomorphic, these AHPL maps, they are becoming closer and closer to being conformal. This guy here is called the maximal dilatation of the map. And when the maximal dilatation is 1, this means that the map is conformal. Okay? And here, the dilatation is becoming closer and closer to 1 because these lengths of these intervals, these are the lengths of those intervals over there that contain the critical point. These are going exponentially to 0 as n goes to infinity. Okay? But let me give you a picture. So the theorem says, if n is sufficiently large, then, okay? So in this picture, I'm going to assume that 2 is sufficiently large. So I can draw the picture, okay? So you have 4 intervals now. And so I'm assuming that I renormalized a lot of times and I got this huge number 4, okay? And the theorem is saying that you can find, a disk around this red interval, which is the interval in that generation that contains a critical point. This disk has size commensurable with this, the length of this red interval, and in such a way that you can iterate this disk and you get 4 other disks around each one of the intervals in the cycle. And then when you come back, when you finally come back, you come back over itself, over the original disk. So the green disks, the last green disk maps onto the yellow disk, okay? In such a way that the map that you get is an AHPL map. It's like a polynomial-like map. And the modulus of this annulus here, you see this annulus here, the yellow minus the green, the modulus is uniformly bounded from below. okay, by some constant. Good. Okay, all right.
The green disk,
What's going on here? What?
green disk may overlap,
The green disk what?
may overlap.
But not in this picture that I'm doing here. You're right. It could, in principle, overlap. Okay?
Because you can take it.
Yeah. I know that. Yeah. But let's not go into that kind of detail. Let's think of them as disjoint like that. Okay? Okay. So from the complex bounds, you can also get C2 bounds for these maps. Okay? Because I'm assuming that the maps are C3. So this theorem is just saying that as you renormalize, the renormalizations become uniformly bounded in the C2 topology on the disks now, on the complex plane. Okay, so here's the problem. To prove the C2 bounds in the real line, the efficient way to do it is, if the map is, say, C3, is to look at the nonlinearity of the map. The nonlinearity of the map is just the ratio of the second derivative by the first, okay? And that's sort of, if you look at the total nonlinearity, if you integrate the nonlinearity, it's actually vanishing exponentially. If you integrate on these unions, on these intervals, you get a sequence of numbers, and the sequence is going exponentially down to 0, okay? And that's how you get the bounds on the real line. But here we are in the complex, so we need to do something. And the maps are not holomorphic, okay? So they're not holomorphic. So what we need, the tool, not new, but I mean the tool that we need is the chain rule for the second derivative of a composition, but in matrix form. It's very important that it be in matrix form. So let me tell you what the chain rule that I'm talking about is. So you have a map, let's say in Rn, which is C2. So if you look at the second derivative as a matrix, is just a juxtaposition of the Hessians of the various components of the map, right? Mm-hmm. So you get a matrix which is n by n squared. So for instance, if you are in dimension 2, which is really what matters to us here, you can write the map like this. Okay, as the real part plus I times the imaginary part. And you can take the second derivative and you get the Hessian of u juxtaposed with the Hessian of v, okay? All right, so that's what the second derivative is in matrix form. Now, suppose you want to calculate the second derivative of a composition of two such maps. So you get this formula, okay? So the second derivative of the composition is going to be the second derivative of the first map composed with the second, or maybe you want to call this one the first and this one the second, it doesn't matter. Times the tensor product of the first derivative with itself. So that's the Kronecker product of matrices, okay? So that's an n squared by n squared matrix. So you see you're multiplying an n by n squared matrix with an n squared by n squared matrix, so you're getting another matrix which is n by n squared. And here you have the derivative, which is just an n by n matrix, and you're multiplying it by n by n squared matrix, you get again an n by n squared matrix. So that's the formula, okay? And the shape of this formula turns out to be fundamental for proving the C2 bounds. Now you might say, what is this, right? I mean, where is this coming from? So I don't know if you, suppose you take this formula and you do something very illegal with it. So let me take this formula. Okay? So I'm going to repeat the formula here. Okay? I take this formula, I'm going to divide both sides by, let's see, I think I want to divide it by d psi, d phi composed with psi, okay? And then I cancel. you know, this is what you should never do, right? Anyway.
Is this step used in the proof?
But I don't know if you can see that you get something which is the nonlinearity of the map. If imagine the map was holomorphic. If the map was holomorphic, this thing that I'm doing here is perfectly legal, okay, in some sense. And what you get is precisely the formula for how the nonlinearity of a composition goes. The nonlinearity of a composition is going to be the nonlinearity of the first map transported as a one form by the second map, plus the nonlinearity of the second map. Okay, so it's precisely the formula for the nonlinearity. So it's not surprising that this formula gives you what you need to get the C2 bounds. And the way the C2 bounds are done now is the following. You have something that you know already happening on the real line. You already have these bounds on the real line. So you take a point which is off the real axis, inside one of those little disks, the renormalization disk, and you follow its orbit, and you shadow this orbit by an orbit which is on the real axis. You have the bounce on the real axis, you have this shadowing, you get the bounce on the complex plane. So this is how it's done, okay?
So to ease the, so you're kind of doing the cancellation of the right factor with the first term and with the left factor on the second term.
Right, right. Yeah, they're exactly.
If these were holomorphic maps, is the nonlinearity the Schwarzian derivative?
No, the Schwarzian is the derivative of the nonlinearity minus 1/2 of the nonlinearity squared for a holomorphic map. So it's something that precedes the Schwarzian. It's something that, yeah, anyway.
That's okay. So you're saying this cancellation and the shadowing argument is enough to prove the lemma?
Well, yeah, that's the moral argument. I mean, you need to do some estimates which are... By the way, what you need to do actually...
ideas.
Right, that's the... So of course, we don't use, in the paper, we don't use the second derivative of a composition of two maps only. We have to iterate the map, right? So you imagine that there's an induction, there's a more horrible formula that I'm not going to show you here, but you can find in the paper.
So say it again, so in the case if it was totally conformal, you have the classic
the standard
situation.
nonlinearity chain.
And then if you iterate, you say you are getting closer and closer to your set lambda. That's going to be conformal.
Yeah.
Are they going to cancel out those
That
factors?
close to the real axis, the map is conformal. Actually, on the real axis, the dilatation is 0.
Yeah.
Right? Because I'm assuming that it vanishes with the distance to the real axis. So at the real axis, the map is conformal infinitesimally. Okay? So anyway. Well, this is just something about notation. So now I can tell you what the theorem was. So I repeated the statement. But, okay. So the theorem says the following, that if you start with a unimodal map which is infinitely renormalizable on the real line, and you know that it's a little bit better than C3. We need C3 plus alpha, it turns out. Okay? And you have some criticality. You know, the criticality is not really important here. 2, 4, 6, whatever. Then if you take any asymptotically holomorphic extension of this map to a neighborhood of the real axis, okay, you can start renormalizing this asymptotically holomorphic extension, and the deep renormalizations are going to have the properties that we want. So for sufficiently large n, if you look at the period of the product of the periods of renormalization up to time n, and you look at the iterate of this map, f, the appropriate iterate of the map, I keep getting lost with this thing. So this iterate here is defined on some small neighborhood of the critical point, right? So you can find a neighborhood such that this iterate will be an AHPL map, okay? Number one. Number two, if you look at this HPL map, it has a Fielding-Julia set, okay? And the periodic points in the Fielding-Julia set are actually, they're all repelling, okay? In particular, the Julia set and the Fielding-Julia set, in this case, they coincide. There are no interior components to the Fielding-Julia set. Moreover, these maps are topologically conjugate to an actual polynomial mapping. So in particular, there are no wandering domains. And you also can do, can do more. You can do some estimates that show that the so-called puzzle, Yocco's puzzle pieces shrink. I'm not going to go into that, but this implies that the Julia set is locally connected. So in the time that I have left, which I think is, I don't know how many minutes, 2 minutes, 3 minutes, I don't know. 3 minutes. I'm going to try to give an idea of what the proof uses. So the proof uses the real bounds, the C2 bounds, the complex bounds. That's not surprising. It also uses the control of the hyperbolic metric, how the map distorts the hyperbolic metric in the codomain of the map minus the real axis. You take the codomain, which is this, you remove the real axis, okay? You get two half disks. These half disks are simply connected Riemann surface. You can put the Poincare metric there, okay? And you want to understand how the metric is distorted by the map. So let me be very concrete here and worry only about this statement here. This statement here, that for large R, each periodic point is repellent. Suppose you have, So suppose you have an actual holomorphic map which is polynomial-like, and you would like to show that every periodic point in the Julia set is expanding, okay, is repelling, okay? So, of course, you could use Montel's theorem, blah, 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 but you're not going to do that. You're going to do, that's the wrong way to do. The right way to do is to use the following principle, which I also learned from Dennis. So here's this domain. I remove the real axis here, okay? So I'm thinking of this y. Y is V, which is the codomain of the map, minus R, okay? And over here, there is the domain somehow. So let me call it X. Now suppose you have a periodic orbit here. So you iterate, and this guy goes to this guy goes to this guy. Maybe it goes down here, and then it comes back, okay? But it stays away from the real axis. The real axis is forward invariant, so something falls in there, it never leaves anyway, right? So take a periodic orbit which is off the real axis. I want to show that it is expanding. So how can I do it? I can use the following principle. These maps, they're covering maps, they're branch covering maps. So there are branches which are globally defined on this upper half disk and this lower half disk. So for instance, draw another picture here. If you take a pre-image of, say, this half disk, you get maybe a quarter disk like this, okay? This is your part of the domain. The map going backwards is a univalent map, so it's going to be an isometry between the Poincare metric here and the Poincare metric of this little piece here, okay? And then you have an inclusion. What? Because it's a univalent map. Okay?
No, it's not holomorphic.
No. I'm saying, suppose the map is holomorphic.
Oh, okay.
I'm trying to give an idea. Yeah, okay. So, in the holomorphic case, it's easy because you say, well, this map going backwards is an isometry, and then the inclusion of this guy inside this guy is a contraction of the Poincare metric. Okay, the Poincare metric here, the density here is much larger than it is here. I mean, at least at points that are close to the boundary. So you have this contraction. So you have isometry and contraction for the map going backwards. So for the map going forward, you have expansion. And you're composing the expansion, so you get expansion. So when you come back, the periodic orbit is repelling, it's expanding. So this is in the holomorphic case. These maps are not holomorphic.
They are quasi.
You're comparing
It's an open problem.
different hyperbolic metrics.
But I have used the inclusion.
And one in the big.
Yeah. Okay, so I would like to use this idea, but unfortunately the map, like Dennis said, is not holomorphic. However, I can factor it as a composition of something which is holomorphic with something which is quasi-conformal and is also asymptotically conformal as I get closer and closer to the real axis. So I'm going to have to do an iteration like this. I'm going to write F as phi composed with G, where G is holomorphic and phi is quasi-conformal. So I'm doing a composition like this.
But only finitely many.
Finitely many of these guys. Okay? But I'm actually going to look at the composition in the following way. I'm actually going to look at it like this. Okay? Yeah. Okay? G. And I'll explain why I'm doing this. So, G expands the hyperbolic metric, but phi could possibly contract. Okay? So I need to show that the expansion beats the contraction as I iterate. And the reason why I'm doing this is that if I have a point and I do phi of this point first, and then I do G, when I do phi, I don't change the scale where this point is relative to the real axis. Because these maps are becoming asymptotically conformal as you get closer to the real axis, so you can use something like a Kurb's principle, okay, 1/4 theorem or something. So I'm going, in the proof we have to divide the codomain of the map into scales, into like strips. I put a bunch of strips like this, and these strips, they have like essentially uniform hyperbolic height, okay, but they're going down this way. And then you have to see what happens when you iterate a point. And every time you are in one of these levels, when you apply phi, you don't change the level too much. You change just a little bit. Okay. Okay. So you need two things. You need so this is the idea, but now you need estimates, right? This is where things get tricky. So you need an estimate on how much expansion you have for the holomorphic part versus how much contraction you can have by the quasi-conformal part. Okay, so these are the two lemmas that I want to give you. Okay, the proof also has to control the sizes of the puzzle pieces to prove the local connectivity, but let's forget about that. It turns out that in the proof of the estimates, I need to use the Slodkowski's theorem of holomorphic motions. I'm not going to talk about that, but basically it's a theorem that says if you have a holomorphic motion of some subset of the sphere, you can extend it to a holomorphic motion of the entire sphere with the same time parameter. Okay, if the motion is defined on a disk. Okay, if it's a motion defined on more parameters, you cannot do that. Anyway, so here's the idea. The idea then is to take. You have to show this lemma or the proposition. You pick a point in the Fielding-Julia set, and you take a tangent vector at that point, and you apply the map and you iterate, okay? And you want to show that the lengths of the hyperbolic lengths, this thing here, this bar with a y there means the length in the hyperbolic metric of y, okay? You want to show that this ratio goes to infinity. That's one lemma that you need to prove. So we use the Stoy law of decomposition, like I said. And again, we need to show that G, the expansion that you get from G beats the possible contraction by phi at every scale. So here's a lemma. I learned this lemma. I actually had to kind of combine a couple of results that McMullen has in his two books. He has like two books about complex dynamics. And he never states explicitly this formula, but I was able to calculate it. This function is a function. All you need to know is that this is a monotone function that goes from 0 to 1 as s goes from 0 to infinity. Okay. So this lemma is saying that if you take a holomorphic map between two Riemann surfaces, hyperbolic Riemann surfaces, one contained in the other, x is contained in y. Okay. And you're looking at the expansion, possible expansion of, the expansion of this map with respect to the hyperbolic metric of y. So it's a quantitative, okay. So version of what I said there qualitatively, okay? So this function is less than 1, so here I'm taking the reciprocal of that, so this is always greater than 1. But you see, what is this s, x, y of little x? It's the hyperbolic distance in y between the point x and the complement of x inside y. So I'm in this situation. I have a point here, and I'm applying the map. Okay? If the point is very close to the real axis, this estimate is not going to tell you much. Okay? It's just because the hyperbolic distance between, so I guess it's the other way around. Yes, if you're very close to the real axis, the distance between this point and the complement of x inside y is huge. So this phi is very close to 1, so you're not getting much expansion. Okay? But in any case, you have an estimate.
Well, what if it's out near where the axis goes out? If it's over to the
If
right?
I'm here, near here, you mean?
No.
Where?
Near the axis, but over near the boundary.
Oh, here.
No, over at the point 1/4 on the real axis.
Oh, you mean here?
No, go over to the right till you get to the boundary.
Oh, you mean here?
Keep the point inside.
I don't know what you're saying. Where do you want
Slide
to
the point that you were talking about to the right, parallel to the x-axis,
Like here, maybe.
and closer. Closer.
Closer, yeah.
Yeah, even a little closer.
I understand what you're saying, but let me say something.
Yeah.
The Julia set that we're interested in is far away from there. The Julia set is inside here somewhere. So it doesn't matter.
Oh, you want to know the distance to what that is?
What?
Well, you use
No,
the
I mean,
argument that the distance.
the estimate continues to be valid. It's the same, you know, if you are here,
Okay,
if you're here,
I don't think I understood the argument.
if you're here, the distance between this guy and the boundary is very small.
Yeah.
Okay? The distance inside y, not inside x. Okay? Notice that the distance there is the distance in y, not in x. Okay. So this lemma is really due to McMullen. Okay? He just didn't write the formula, but we needed the formula.
Inside x is infinite.
What?
Inside x, the distance is infinite.
What do you mean inside x the distance is infinite?
No? Hyperbolic
It's
space.
in y.
No, x is contained in y. I'm taking a point in x, and I'm looking at the distance between x and the complement of x inside y. That's always a finite
Which
number.
distance? The y distance?
The y distance. It's always a finite number, but it can be very big if you're very close to the real axis. Okay? All right, so this is the key lemma to bound the expansion. But now I need to tell you how to bound the contraction, and that's where things get really more tricky. Okay? So you need to know how much distortion the quasi-conformal part brings you. Okay, I'm sorry. Let me just. So there is always this relationship between how a quasi-conformal map distorts lengths, infinitesimal lengths, relative to the quasi-conformal distortion of the map and the Jacobian. This formula you can write it in Euclidean, using the Euclidean metric or the hyperbolic metric. The formula, the inequalities are going to be the same sort of formulas. Here I'm using the hyperbolic Jacobian, okay, which is just the regular Jacobian multiplied by the ratio of the densities in the image and the domain squared. Okay? So this means that in order to bound the distortion of lengths here, this guy here, I need to bound the Jacobian. Because the quasi-conformal constants, they're actually going to 1 as you renormalize. They're really bounded. Okay? All right, so I promise not to bother you after this, with these inequalities. Let's forget this. Let's imagine that you have a fixed point, just to be very concrete. Suppose you have a fixed point of a map, which is a self-map of the disk, and this self-map is a C2 quasi-conformal diffeomorphism. Okay? It's a C2 diffeomorphism, so quasi-conformal. If you have a fixed point, this condition here is completely empty. It doesn't say anything. So suppose you know that this phi is getting closer and closer to being conformal as you get to the boundary of the disk. So in other words, suppose that the dilatation of the map near the boundary is vanishing with the distance from the boundary raised to some power beta. Okay? Then the Jacobian is also very close to 1. So morally this is saying the following. If the map is almost conformal near the boundary, it's also almost an isometry or almost an area preserving map, okay? So that's the idea. So we have to prove this. And then using this estimate and juxtaposing it with this estimate, where is it? With this estimate, you can show that G always, the expansion given by G always beats the possible contraction by phi. Okay? So you gain and you are able to show that the periodic points are repelling. So that's the easiest statement there. Then you have to show other things. You have to show also the puzzle pieces shrink, so you get local connectivity and so on. But I just wanted to give you a flavor of what is involved. And I believe that this kind of estimate here, this estimate here, might have applications in, I don't know, Riemann surface theory, because when you go and look in books, people talk about quasi-isometries. You know, but in quasi-isometries, the statements are always macroscopic, and there is always some constant being subtracted from both sides of the inequality. So it's not very useful here, because here we are really looking in the small. We are looking infinitesimally. Okay, so this is a quantitative version of this sort of idea that, you know, something which is almost conformal is also almost an isometry.
It's like by Lipschitz.
What?
It's like by Lipschitz.
Well, they are by Lipschitz, but I mean, yeah, it's like that, yeah.
My wishes with respect to what?
With respect to the metric that you have there, for example, yeah, the hyperbolic. I mean, in the small, the hyperbolic and the Euclidean there, right? I mean, near a point there, equivalent.
But your other statement about the quasi-isometry having added a constant, you can, well, if you're in some nice domain, you could always go to the boundary and then go back, and then it's by wishes with respect to.
Yeah, well, I mean, there's lots of things you can do, but I'm saying
Yeah.
just being by Lipschitz is not going to give you what you want here, you know. Anyway, so here's just some references. If you like to look at the paper, it's already available in the online version of ergodic theory. The paper by Trevor Clark, Sebastian Van Strien, and Sophia Trewitz in Communications, and as you can see, it's a very long paper. Okay. And the paper that I mentioned, the ugly paper that I mentioned that I'm not happy with, is this paper here. And the idea, some of the ideas about almost conformal maps, you know, near the real axis and so on, they have some intersection with this paper here, okay, by Pablo. Pablo was the last graduate student of Wellington.
Of De Mello.
What?
No, you said Pablo was the last student of Guarino, of himself.
I said
Oh, he
Pablo
said
was the
Wellington.
last student of Wellington.
Ah, well.
Yeah, did I say it wrong?
No, I understood.
Okay. So, thank you. Yeah.
Would you say if you were in the polynomial case, we use the external ray or equipotential to construct the renormalization domain?
Mhm.
In your setting, how do you sort of
Okay, so
present
that's a good question.
Can you repeat it?
Yeah, well, he's saying that in the holomorphic case, the way you define the puzzle pieces is by taking an external ray. You take the Riemann map from the complement of the Julia set, or the Fielding Julia set, and you look at like equipotentials and rays coming from infinity, and you use those to define these puzzle pieces. And he's asking, here you don't have that because the map is, right? I mean, well, one way to get something invariant, because it needs to be dynamically invariant,
Yeah.
is you take the annulus, which is like a fundamental domain, and you foliate the annulus by lines joining the two components, and then you iterate backwards. And as you do that, you can start getting these curves, and you can show that because the map is asymptotically holomorphic, these rays are going to land, and you're going to have your puzzle pieces. So that's the last part of the paper.
You still use the localization map at the repelling fixed point, and then locally you have those similar.
Localization map, you mean what?
At the repairing fixed point.
Yes, you start.
Repairing periodical points.
Absolutely,
You look at
yeah,
the
I should
local
have,
one,
yeah.
And you can cuts there.
Right, you have to start with the guy who joins the, you see there is like a rightmost fixed point for the map, and you can look at the, a line going from there to the outside, okay, and then you're looking at that line and you're kind of iterating it backwards.
Yeah.
That's what you're saying.
Yeah.
Yeah, we do a similar thing here, okay? All right.
Any other questions?
Yeah.
What are the 4 more slides you have?
Oh, I see. It's the history of this. I should have started with this, but you know, I messed up because I didn't bring my laptop with me. I only brought my tablet, and I wanted to move this to the beginning. I should have told you this story before. I don't know if you want to hear it, but it starts with experimental discoveries by numerical discoveries by Collet, Trevor, and Feigenbaum in the same year, 1978. Basically what they did is they look at these one-parameter families, like the quadratic family, x goes to lambda x times 1 minus x. So these are the maps that I was drawing before, but you know, when you have a one-parameter family, you start having no dynamics, you know, only an attracting fixed point here. Then at some point you develop another attracting fixed point. This attracting fixed point, at some value of the parameter, it bifurcates into an orbital period 2. And if you keep increasing the parameter, the orbital period 2 bifurcates into an orbital period 4, and so on. So if you record the parameters, you get a sequence of numbers converging to some limiting number. And if you look at these intervals, consecutive intervals determined by these sequence of points, and you take the ratio between consecutive intervals, this converges to some universal number, which is now called the Feigenbaum constant. Okay, and it's universal in the sense that it's independent of the family that you pick. Okay, and this was observed by Feigenbaum.
That's crazy.
It is crazy. Yeah, from some arbitrary, essentially arbitrary one-parameter family of maps that look like this, you get the same number. Okay. This is a fantastic discovery. In the paper by Collet, Trevor, they also examined the structure of the... At the end of this cascade of period doubling bifurcations, you get a map that has the property that the critical point is no longer periodic, it's like recurrent on a Cantor set, which is exactly the situation I was telling you here. And they examined the structure of this Cantor set, and they see that, you know, the ratios and so on, as you go down, they become also universal. Okay? So in particular, you have like a universal Hausdorff dimension for these guys and so on. So they propose an explanation that, you know, that there should be some kind of what they call a period doubling, a renormalization operator lurking beneath this. And shortly afterwards, Lanford was able to produce a computer-assisted proof of this. But of course, computer-assisted proofs are not very enlightening. And then Campanino and Epstein produced a proof of the existence of this universal map at the end of this cascade. But Dennis always told me that there was a secret moment where they kind of used the computer, right? They used some estimate, which he only knew by some computation or something. Anyway. But it's just a proof of existence. It doesn't show you, you know, you want to show that there is some hyperbolic picture near this fixed point. Then this guy Davy came along, and he's not a dynamicist, he's a guy in functional analysis, but you know, this is a very hard paper, short paper, but very hard paper, where he takes this hyperbolicity that Lanford found, and he pushes it to the world of C2 plus Z from maps near this fixed point. And then people realized that the situation was actually more general, that you actually had like a Cantor set of universal maps, and that there was a larger renormalization operator that had the property that this Cantor set should be like a hyperbolic Cantor set, and that the dynamics would be like a full shift in a finite number of symbols. I'm thinking of a bounded type situation. And the challenge was to find a conceptual proof of this, and this is where Dennis came in. Okay? So this is the major breakthroughs. First by Dennis, with the real bounds, complex bounds, with the convergence towards the attractor, but without a rate. Then McMullen was able to show that the convergence towards the attractor is actually exponential. Then Lyubich was able to prove the full hyperbolistic, but in this funny world of quadratic-like germs modulo affine. And then more recently, or still not so recently, Avila and Lyubich found another way of proving the exponential convergence, because this work here, this work of Lyubich, also uses McMullen. Okay? But now there's an independent proof due to these two guys, which doesn't use that. Okay? And it's a very nice result, and so on. And in 2006, Wellington, Alberto, and I, we were able to push this hyperbolicity to the CR world. And what we did is basically we went to read this paper by Davey, and we kind of tried to adapt what he was doing there. He was doing that just for the fixed point. We had to do what he was doing relative to the entire attractor of the renormalization operator. So that's it's a mess, okay? So it's ugly. But we went a little bit beyond the conjecture, because we also show, this operator has this attractor, the points in the attractor, they have these stable manifolds, and we show that they are actual manifolds in the CR world. And they form a lamination, and we show that transversally this lamination, if you take a typical transversal to this lamination, so you're going to get, so that's a one-parameter family of maps, you're going to have those points where you have the same topology as the, the points that you get there, they're precisely the maps which are infinitely renormalizable, and this scatter set has a universal Hausdorff dimension. You can kind of move around, because you show that the holonomy of the lamination is C1 plus beta for some beta. Anyway, it's kind of messy, and we were never really happy with that, so that's why we were trying to understand these asymptotically holomorphic maps. So that was the history, not so much. Anyway.
Do you still want to mention the open problem if the exponent is not an integer?
Oh my God, yeah, right. Yeah, so everything that's done here is for integer exponents. What? Even integer, yeah. Even integer. But imagine that you have maps which are, they have a different, they have a criticality which is not integral, but it's like coming from both sides, the same exponent set. Okay?
Yeah, like a Roman arch.
What?
Like a Roman arch.
Yeah, well, it is going to have zero tangency there, but I'm saying, it's not going to be, it's not going to be
like x to the 1.5.
Right, like x to the 1.5, yeah. Okay. So,
and the theorem is true there, but unproven.
Yeah, well, the existence.
It's a very interesting point. Different groups of physicists already in the 80s, whatever the exponent was, they get this universal behavior.
Yeah.
This guy computes it, that guy computes it. So no question that there's not a theorem.
It's definitely true, but
40 years later, we don't have a proof.
We don't have a proof. We don't have a proof. We only have a proof of the existence of the attractor. That's like Martin's, right? He was able to show that the limits exist and so on. But you don't have any convergence, at least nobody knows anything about
We
that.
have real bounds.
Oh yeah, we have real bounds, but yeah, right. We do have real bounds, but
Yeah, you need an argument that uses the real bounds.
Right.
You have the real bounds.
yeah, that's probably the major open problem.
So if you could do your theory for different exponents, you'd have it. Right?
What?
You could do this theory for other exponents, you would have it.
Yeah. This is, but so far we're not able to do this. Anyway. I think